Swayam Prabha. Digital India. Educated India.
In the previous classes, we were looking at some numerical methods by which we can solve the position and momenta of an n-particle classical system. For instance, we discussed about Geer's predictor corrector method, where you can expand the position and the velocities as using Taylor series expansion, and then you do it in two steps. First, we predict a position and velocity, and then we correct in the second step. In continuation with this discussion, we will discuss few more finite difference methods which are commonly used in many MD simulation packages and softwares. So, in this class we will talk about a set of algorithms known as Verlet algorithms. We have to remember that all these finite difference methods attempts to solve the second order equation governing the equation of motion, where here I stands for every particle, ith particle, m here is the mass times the second derivative of position, in other words the acceleration. So, the mass times the acceleration is given by the force. And so, in the Verlet algorithm, what we aim to do is, first we expand using Taylor series expansion for position at t plus delta t about r at time t. So, here what we have done is, we want to update the position at t plus delta t using the information at the position at t by expanding using Taylor series expansion about time t. So, the first quantity here is the position at time t, and the second quantity here is the delta t times the first derivative of position, which is velocity, and the third term here is the second derivative of position with respect to time, which is nothing but the acceleration. And then we can ignore the higher order terms in this equation. And then similarly, we can also write r at t minus delta t, that is, so you are looking at time at t, and then you want to go to the, you want to predict the position and velocity at t plus delta t. For this, we are trying to write Taylor series expansion. Similarly, using this quantity at time t, we can also write what is going to be the position at t minus delta t also, using same Taylor series expansion. Like this. So, now we call this equation 1 and this equation 2. Now, if I add this equation 1 and 2, you can see this velocity can be eliminated from this set of equations. So, adding equations 1 and 2, we get on the left hand side r t plus delta t plus r at t minus delta t is equal to 2 times r of t. You can see this plus term and minus term will cancel. So, we have only the even power terms. And then what is left here is terms which are of the order of delta to the power 4, because anyway all the odd powers are cancelled here. So, from here we can write r at t plus delta t is equal to 2 r t minus r at t minus delta t plus delta t square a of t, and the errors are of the order of delta to the power 4. So, this is the equation that we use to update the particle positions at a time t plus delta t. And if you look at what are the things we are using the current position at time t and the previous position, that is at t minus delta t, and we are also using the acceleration at time t. So, these are the quantities we use to update particle positions. One of the interesting feature about this formula is that we have eliminated the velocity, but in actual simulations we may want to measure kinetic energy or velocity dependent properties. So, we are also interested in obtaining what is the velocity at time plus t plus delta t. So, to get velocity, all we need to do is again take this equation 1 and 2, instead of adding them you subtract them, thereby you can retain the velocity term. So, now subtracting two from 1, you will get you can see the first term r of t will get cancelled, and what is remaining there is 2 times delta t times v of t. Similarly, the acceleration term will also cancel, and then you are left with only order of delta t to the power 3 terms. So, from here you can solve for the velocity at time t as r at t plus delta t minus r at t minus delta t divided by 2 times delta t, and here now the error becomes delta t squared because you are dividing by delta t all over here. So, the accuracy of the velocity calculation is obtained up to an error of delta t square. Yes. So, what we can show is that the way we updated the particle position and velocities can be shown using this particular diagram here. What is shown here is that on the column you have times, and then in the row you have positions, velocities and acceleration. This diagram basically says how we advance the particle position and velocities in time for various algorithms. Right now we will work with the first row, that is this, which is for the velocity just the Verlet algorithm. So, here you can see that what we are first doing is we take the position at t, r of t, that is this, and then we also use the acceleration at t, that is this term, and then we also use the position at t minus delta t, that is this term. So, we are using these 3 terms, position at t, position at r minus t and acceleration at t. So, using these 3 quantities we are updating the position at t plus delta t. Okay. So, that is what diagrammatically shown here. And then if you want velocity, as I said before, you can use the position the new position at t plus delta t and the old position at t minus delta t, and then you can get the current velocity at this particular point. Okay. That is how this algorithm evolves in time. So, in this diagram this is basically a pseudo code that says how this algorithm works. So, what we do here is that at any given point of time t, you can see that we are obtaining the new position, that is at r equal to t plus delta t, using the current position and the old position and the current acceleration. So, you can see that is being done here. So, the new particle position here is stored in a variable called rx new I. This is 2 times the current position. So, this is basically r at time t, this is r at t plus delta t, and this is r at t minus delta t. So, you can see that this equation is basically represented in this particular line, and this is delta t squared, and this Ax of I is basically A of t. So, this is done in a component form. So, first we do for x component, then y component and z component. So, these 3 lines is basically a position update for t plus delta t. And then for the velocity at time t, we said we could use r plus minus r at t minus delta t by 2 delta t, and so you can see that that is basically done here. So, this is our new position, that is r at t plus delta t. This is the old position at t minus delta t, and this is divided by dt2. So, this variable dt2 is nothing but delta t by 2. Velocity is also updated component wise for the x component, y component, z component. So, at this particular loop we are able to get new positions, also the current velocities at time t, and then if you want to calculate kinetic energy, then you can calculate the sum of the velocities, square of the velocities, and then you can get the, for the linear momentum you can get the sum of the velocities. At this point, after updating the position, we have to store the new positions. So, what we are trying to do here is, in the old position, so this is we are basically updating the Rx old with the current position, that is at t, both all for x, y, z component, and then whatever we have calculated at t plus delta t, that we are storing as a current positions. Thereby we do not have to, so every time you update r plus d plus delta t, you can actually put the r of t in the old position and r at t plus delta t in the current positions, and then you iterate over to the next time step. You update the time and then go to the next time step and then do over this. So, this is how one would actually write the Verlet algorithm in a code. And if you look at this Verlet algorithm, it has several interesting features. The first thing to note here is how many variables it is storing. Okay. So, storage is basically, we need to store r at t, r at t minus delta t, and a at t. So, these are the 3 variables that we need to update the positions. For each of these variables there are 3 components. So, essentially you are talking about 9n. So, there is going to be 9n storage, 9 variables are to be stored. And the second thing is, you will see that if I look at the position update at r plus delta t, you can see that this is actually has a time reversible property, because this is time reversible, because if I substitute delta t as minus delta t, you see this equation remains unchanged. Okay. So, it has time reversible property, and it also shows very good energy conservation. You have to remember that the velocity was of the order of delta t square. So, that means we are truncating higher order terms in velocity prediction. So, this is going to add some drift in the kinetic energy. So, it is not strictly conserving kinetic energy, but it does reasonably well in terms of conserving energy, and then this linear momentum is conserved. So, these are some of the features of this particular algorithm. As we noted already, for periodic box, the angular momentum anyway is not conserved for any algorithm, that is understood. And the other important thing is, unlike the predictor corrector method, which involves 2 stage, the Verlet algorithm updates the position in single step. It is a single step algorithm. So, these are some of the features of Verlet algorithm. So, the next algorithm we will talk about is what is called this leapfrog algorithm. So, first we try to update velocity at a half step. So, delta t is our time step, but we take a mid time step of t plus delta t by 2. At this particular point, we update the velocity using the velocity at t minus delta t by 2 and then using the current acceleration. So, this is the algorithm that we are talking about, which is a leapfrog algorithm. So, you can see that we are using the acceleration at time t and then the velocity at t minus delta t. Using these two information, we get velocity at t plus delta t by 2. So, that is the first step. Then we update the particle position using the current position and the newly calculated mid step velocity, which is t plus delta t by 2. So, this is shown here pictorially. So, we have got the mid step velocity we have calculated just now, and then use that and also the current position, that is r of t. So, using these current position r of t and the mid step velocity newly calculated, using that we calculate the particle position at t plus delta t. And then now we want to again update the velocity at t using the average of the two mid step velocities. And this is shown here. So, you take the two velocities, that is the velocity at t plus t minus delta t by 2 and the velocity at t plus delta t by 2, using these two average and then get the velocity at time t. So, in this particular algorithm, if you see what we have been storing, we are storing the a of t, that is this, and then r of t, that is this, and then also we are storing the velocity, mid step velocity, that is delta t by 2. Thereby this will have 9n variable storage. And we call this as a leapfrog because what we first do is we leap, or we try to predict the velocity in advance in time before the position is updated through this step. So, at this point we only know what is the position at r plus r at t. Okay. So, now we leap forward to get the velocity at the mid time step delta t by 2 using the current acceleration and the previous mid step velocity. And once this is done, now we leap forward to get the position at r plus t plus delta t using the mid step velocity that is newly calculated. So, instead of calculating velocity in the position at same times t or t plus delta t or t minus delta t, we advance first the velocity and then we advance the particle position over the velocity. So, we leap forward over one variable over the other. So, that is why it is called leapfrog algorithm. And the third important algorithm is known as velocity Verlet algorithm. This is very commonly used. So, the schematic for the velocity Verlet algorithm is given here. So, so this algorithm is actually executed in two steps, just like how we did in a predictor corrector method. In the first step or the first stage, we advance the particle positions using the current positions and the current velocity and also the current acceleration. Okay, so that is pictorially shown here. So, use the current position, current velocity, current acceleration, all these things are used to advance the position at t plus delta t. That is the first step. So, now with that you have a new position, we can calculate the mid step velocity. So, this mid step velocity calculation is shown here by this small arrow here, where we use the current velocity v at t and then the current acceleration at a of t. Using these two, we calculate v at t plus delta t by 2, that is a mid step velocity. And then in the second stage, now that we have got the new position, using the new position, we calculate a of t plus delta t. So, remember this a of t plus delta t is the acceleration, and the acceleration is obtained by calculating the forces at that particular time point using the new positions. So, once you have the new accelerations, then we can advance the velocity at t plus delta t using the previous half step velocity plus the new acceleration that we have just found. Okay. So, remember this is the newly calculated acceleration from the new position that we obtained here. So, pictorially this is shown here that using the mid step velocity that we calculated here, okay, that is right here, and then using the new acceleration, using these two we advance the velocity at t plus delta t. So, at the time t plus delta t, we have the position, velocity and the acceleration, all of them calculated. So, in this case also you can see that since we are using r of t, v of t and a of t, then we are talking about 9n variables of storage. And it has two, as I said before, it has two stage updating of two stage updates, and then this particular algorithm seems to be very good in terms of numerical stability, accuracy and also simple to code. So, because of all these nice features of velocity Verlet algorithm, it is also good in predicting the velocity, because that it takes the two step accelerations using the current acceleration as well as the new acceleration, because of which the prediction of the velocity is more accurate than the other previous algorithms. So, because of which it has a better stability, accuracy and it is also simple to code. So, this is one of the widely used algorithms in MD simulations. And there are many other algorithms, but one final algorithm I want to talk about is what is called this Beeman algorithm. So, you can see that most of these algorithms are basically a different version of the original Verlet algorithm with slight modifications to improve accuracy or to improve numerical stability. So, in that light, the Beeman algorithm goes like this, where the particle position is updated using the current position and the current velocity and the current acceleration with certain weightage factor, and also using the acceleration from the previous step, that is at a t minus delta t. So, you can already see that we have to store r of t, v of t, the current acceleration, also the previous accelerations. So, you may recall that in the Verlet algorithm we used the previous positions. So, in this algorithm we are using a current time step, a current position, current velocity current acceleration, but also the previous acceleration at time t minus delta t. So, so what we are storing are four quantities or 4 variables. So, 4 times 3. So, the storage would be 12 n variables. So, it requires more storage space compared to the other algorithms. And then once the position is updated, then we can also update the velocities at a time t plus delta t using the following formula. Again, we use the current velocity. So, to get this new acceleration, you would be using the new position for this. Using the new position, we calculate new forces. From the new forces, we calculate new acceleration. And it also depends on the current acceleration. So, basically this Beeman algorithm basically attempts to improve the calculation of velocity as accurately as possible, because of which it uses many quantities. It uses the current velocity, new acceleration, current acceleration, and also old accelerations. So, because of the combination of accelerations of 3 different time points t, t plus delta t and t minus delta t, the accuracy of velocity calculation or the kinetic energy calculation in this algorithm is little better. So, the energy energy conservation is much better in this case. So, better energy conservation and accuracy, of course. So, now what I am going to show is now that we have looked at different kinds of algorithms for solving the second order ODE of the equation of motion, we can now check what is the relative performance of these algorithms with respect to different time step. Okay. So, this particular diagram is actually obtained for a Lennard-Jones simulation of Lennard-Jones fluids certain. So, so here what we are plotting is a simulation with Lennard-Jones potential. So, it is NVE Lennard-Jones simulation done with different algorithms and for each algorithm we use different delta t values. The objective is to find which algorithm is better by calculating the energy drift or the fluctuation in the total energy as a function of delta t. So, since it is an NVE ensemble, strictly speaking there should not be any fluctuation in energy, this should be 0, this quantity should be 0 for an NVE simulations. However, as we noted in various finite difference algorithms, we have round off errors because we truncate the higher order terms in delta t, and this accumulates error, and this will show up in the energy conservation. So, now you plot based on various simulations done with different algorithms, and for each algorithm using different delta t, we measure what is the fluctuation or what is the error in the energy from the fixed energy scale. And so, what is shown here is this particular line is the velocity Verlet algorithm, and this is the gear predictor gears method with the 4th order, this is 5th order, this is 6th order. So, the gears, the 4th order, 5th order, 6th order method basically means you basically keep multiple terms in the expansion for better accuracy. So, if you see that when the delta t is very small, you can see that the higher order gear algorithm seems to do better because they have the least values of the energy error in the simulations. Whereas, if you look at the higher, okay, so for larger delta t values, okay, so that means if you look at this particular region, it seems that the higher order gear algorithms are giving a larger error in the energy compared to the velocity Verlet algorithm. So, because of this we often use a velocity Verlet algorithm in the MD simulations rather than any of these higher order methods like Gear's predictor corrector methods. So, the reason that at higher delta t, the reason that these higher order terms are not really performing well is because if you recollect, this Gear predictor corrector method works on expanding the position and velocity using Taylor series expansion in time. And then, but if you actually look at MD simulations, the way it works is that you have intermolecular forces coming from the neighboring molecules, and in a given delta t time step there are many molecules going in and out of this neighboring zone, and all these informations are not taken into account when you go to higher order Gear's algorithm. So, if you go to higher and higher algorithms, there is not much improvement in the calculation of the positions and velocities. So, because of this we want to restrict to simple algorithms like velocity Verlet algorithm, which can be done in just 2 steps with a minimal storage. So, because of this, most of the MD simulations that you use, LAMS or GROMACS, any of those would typically use some variation of the velocity Verlet or Verlet algorithms in general. You very hardly see the usual algorithms like Runge-Kutta method or Gear's predictor method for MD simulations, because such a sophistication is not really relevant for MD simulations as such. So, what I was saying is, do you understand what is the meaning of this plot? I mean, what I am plotting here is basically, so what I am doing is we are doing a Lennard-Jones fluid and then in a NVN sample. Okay. So, since I am fixing the energy constant, the fluctuation in the Hamiltonian should be 0 in principle, right, because it is a constant energy simulations. However, when we try to produce a trajectory using finite difference methods, we have this higher order terms which we are neglecting. Okay. So, because of that we are basically the trajectory is not exactly accurate. There is going to be some error in predicting those trajectories, because of which there will be some finite values of energy fluctuations or energy conservation is not strictly followed. So, you basically ask what is the energy drift or energy loss, or what is the energy fluctuation because of the use of the finite difference method. Now, one of the way you can actually compare and contrast between different numerical methods is by plotting what is the error in energy that is propagated because of finite difference method, and how that fluctuation or how that error is scaling with the delta t. You would expect when delta t is very small, you would expect this error will be close to 0, and you can see that over here across all algorithms, whether it is velocity Verlet algorithm or Gear's predictor corrector method, you can see that as long as you go to very small delta t, again I have to remind you that these delta t is actually in a reduced quantity. You may recollect that we have defined reduced time for Lennard-Jones units. In these reduced units, we are talking about a delta t of 10 power minus 3, for which the energy the errors are really small, okay, of the order of 10 power minus 5 or 10 power minus 6 minus 7. That is the order of magnitude. This is also with respect to the non-dimensional energy scale. However, if I increase the simulation, if I increase the delta t in my simulation so that I can do faster, I can do simulation faster, you can see that as I increase this delta t, all these algorithms shows increase in the energy, error in the energy, which is supposed to be constant. And what I was trying to tell here is that if you go to higher delta t values of, let us say, of the order of 10 power minus 1 or 10 power minus 2, it seems that the Lennard-Jones system, for the Lennard-Jones system, the velocity Verlet algorithm was giving a lower error compared to the higher order Gear's predictor method. So, that means when you use larger delta t values, we are not really gaining any accuracy improvement through a Gear's predictor corrector method. Okay. So, generally what one should do is, if you want to be very careful for your system, you pick up 1 or 2 algorithms and calculate delta t versus error in the energy like this plot. This will tell you what is the accepted tolerance value for the error in the energy through which you can calculate what should be the delta t. Okay, so that's what I was trying to tell you here.
What will be the order of truncation when we are using it MD simulation?
If you look at the Verlet algorithm, the very first algorithm that we talked about, you can see the position is of the order of the error is of the order of delta to the power 4, whereas for the velocity it is delta to the power 2 delta t square. Okay, so the the Verlet algorithm does very nicely with regard to prediction of the position, but not so much about the velocity. Okay, so that's why we started looking at other algorithms. So if you look at what are the terms that we are keeping and what are the terms we are eliminating, you can find out what is the order of the truncation error, okay, in each of this algorithm. And the last algorithm which I showed, I think it's not really, it didn't record here. Maybe I will write it down because I want to share this to you. So in this algorithm you could have noticed that we are updating velocity using 3 different accelerations at time t, t plus delta t, as well as t minus delta t.
Sir, how could be this linear momentum conservation be concluded from the Verlet algorithm?
So it is basically measured and found to be conserved. So I don't see any theoretical proof as such, but it is mentioned as this is kind of, it guarantees linear momentum. So if you look at this algorithm, you are actually calculating that the velocities, sum of the velocities, which is basically going to be the linear momentum. I can look it up. If there is any actual proof. We want to know about these algorithms because if you look at LAMPS or GROMACS or NAMD or various other algorithms, different softwares use different integrators. You may not have all the integrator available in each of these softwares. For example, if you use GROMACS, I think it allows only leapfrog method, whereas LAMPS would allow you use Verlet algorithm. Okay, so I am telling all this because when you use this software in the future, and then when you have a choice of various method, then you can actually assess which method you think would be right, and you can actually do a simple calibration like the one I said in the last slide by running a short simulations under NVE case. Even though what is shown here is for Lennard-Jones, if you have a different intra and intermolecular forces, you can actually do this kind of tests for your own system by running a bunch of simulations, short simulations, by measuring what is the error in the energy versus delta t using various algorithm that is available at your disposal, and then you make a judgment what to use. Okay, for example, if you get this kind of a graph, you can see that velocity Verlet algorithm seems to be pretty good because it allows a larger delta t, at the same time reasonable accuracy compared to gear predictor method. Okay, so one has to do this kind of a calibration before you start your actual simulation. So that's the point.